think that there's still a little bit of ambiguity on the answer the question of, if not fossil fuels, then what is going to meet people's energy needs? And John's going to take us on a tour of low carbon energy systems. So very glad to have you here, John. And thank you so much for joining us.
So what I'm going to present to you today is the culmination of the last 8+ years of experience working in the space of energy and renewable energy systems, and really kind of share as much of this knowledge as possible at a 101 level, just to make sure that when you engage in your next conversations, that you're doing so from a much more detailed perspective as to what's possible and what's not possible, because the more options that you have available to you, the more likely you're going to find a solution that suits your needs. So we're going to use this slide as an agenda, essentially. This slide also represents all the technologies that we are currently studying and or designing into projects as we speak. So as I mentioned, we started with district energy. I'm not going to get into the details yet. We have a whole section for each one of these primary disciplines, but these are all the ones we're going to be covering in terms of district energy, wastewater energy exchange, industrial heat capture. We're going to get into the geo-exchange flavor, as I call it, of geothermal. Geothermal is actually a category, but we're going to focus on the geo-exchange specifically. We're going to talk about biomass. I'm sure there'll be a lot of interesting eyebrows raised when we get to that one. And then air source heat pumps, which I think a lot of people on this call, I'm just going to presume, are familiar with. Down below, we have what we call complementary disciplines. Energy from waste is down here simply because this is mega scale projects. You don't do this at a community scale. This is a much larger scale type of project. And same with biogas. So we can do the study work in these areas, but as soon as the rubber kind of hits the road, large mega engineering, procurement, construction, or EPC companies typically take on these types of projects, and we stop getting invited to those meetings. And then I put solar down in complementary, but I'm realizing I need to update this slide. The reason why we have it in complementary is historically Rathco has worked in medium to high density types of projects. We're now starting to get a lot more work and experience applying these types of strategies and processes on low-rise projects, and solar can play a much more significant role in the solution to decarbonization at the low density scale of real estate development, but it's much more in a complementary aspect when we get into the medium to high. And it really just comes down to solar has what I call a geometry problem, in that if you just think of a simple cube and you, as a home, and how much volume is in that cube versus how much surface area can I put panels on to collect solar energy, there's a ratio there. And the ratio for a single family home is pretty good. I can get a fair amount of solar panels on there to tackle the energy needs within that cube of space. But as soon as I take the corners of that cube and I start to stretch it into higher density type buildings, that ratio starts to fall off a cliff rather aggressively. And the solar is not going to be able to completely decarbonize the solution. We'd have to cover every square inch of the building, and even then it wouldn't be enough by significant margin. So that's why we've kind of structured it this way. Before we get into the technology, I think it's really important that we kind of set the context and the stage here. I'm building a bit of a reputation as an elephant introducer, so why stop now? When we're talking about decarbonizing buildings, the elephant in the room is space heating and domestic hot water, as you can see here. So this is residential end use on the left, and this is commercial end use on the right. But you can see it's quite obvious that when it comes to space heating and water heating, the vast majority of the GHGs coming out of our buildings are there. And you'll notice that the smaller ones are much more electrically focused types of loads. So appliances and lighting and space cooling. And although we absolutely have to decarbonize our grid, and this is something that hopefully isn't something that's going to happen, you're going to get a much better return on your time investment in terms of trying to get the carbon out of your building if you focus on the thermal aspects as opposed to the electrical aspects. It is the massive elephant in the room. I know we're going to be talking about technologies here, but I think it's really important for everyone to understand that we're all human beings, and human beings are complicated. And so the way I try and explain feasibility to a new client of ours is feasibility has three major layers to it. The first and foundational layer is the technical layer. So this is the thermodynamics, the physics, the engineering aspect, just the basic math associated with what a building needs versus how are we going to serve it with energy. And this is a non-negotiable layer. If it doesn't work technically, it just doesn't work. So this is where our specialty is and where we focus and our talents are. The next layer, though, let's say everything passes the test, where the physics makes sense, the thermodynamics makes sense. The next layer is the financial sense. So there are hundreds, if not thousands, of things that we could be doing in buildings that if we had an unlimited budget, we would absolutely do, but we don't have unlimited budgets. So the next question is, of the things that are technically possible, which ones are financially possible? And as you can imagine, that shortens the list. But there's this third layer that is rarely addressed in feasibility scope statements, which I'm just calling the people layer. And this is where human biases come in. This is where culture comes in. This is where politics comes in. And I've been in this industry long enough that to know that having a solid technical and financial layer of a project is not enough to get that project greenlit and approved and moving forward. Frankly, that is just the prerequisite. Like, you shouldn't even be engaging in any project that doesn't have a solid technical and financial foundation. But unfortunately, that means that your work is just beginning. You really need to then focus on getting the human beings involved in these projects on board and in alignment with this type of project to move forward. And this type of webinar is a massive important step in that process, because if the group that you're trying to get to agree, and as you can imagine, getting a group of people with different interests to agree is already a challenge. But if they're doing that and they're not educated or aware of what the technologies are or aren't or can do or can not do, then you're really at a disadvantage of getting everybody to agree. And so what we find is actually human bias is one of the biggest obstacles when trying to get a bunch of different stakeholders to agree on a path forward to decarbonization. And these are the three biggest biases that we come into. So we'll start with the choice overload bias. There are very intelligent, very educated professionals who have spent 20 plus years working in their respective industries that have never asked the question or been asked the question, what do we put in this building other than a natural gas boiler? It's not even a question asked a lot of the times in these types of real estate development circles. It was just always a pre-gone conclusion that you're just going to put a penthouse mechanical suite on the rooftop, and it's going to have natural gas boilers for heating and some chillers or fluid coolers for cooling, and away we go. The engineer just needs to size it, and there was no discussion about alternative technologies. Now that we're trying to decarbonize buildings, there is no direct substitute for a natural gas boiler from a technical perspective. There is no piece of technology that I can just take off a shelf that's going to be able to perform at the temperatures, at the dispatchability, which means I can just turn it on and off whenever I want, at the price, both in terms of the upfront capital plus the operations. There's nothing out there that I can just pull off a shelf and say, instead of a boiler, do X. In addition to that, there's a list. There's a whole list, which is what this webinar is all about. So you have this choice overload bias. You've ever been at a restaurant and you look at a menu and there's just so many options, you don't know which one to pick or even how to assess which one's good? That's a real problem that we're seeing in these types of projects. The other bias that we're seeing is the optimism bias. And the optimism bias is, we got lots of time. We're going to figure it out. Don't worry. We can just keep doing the business as usual on this project. We'll figure it out on the next one. Or it's like, that's not my problem. That's somebody else's problem. They're going to figure it out. Don't worry. Or, oh, hey, the next Elon Musk, he or she will be born anytime now, and they're going to invent this new thing, and it's going to save everything. It's all going to be fine. It's all going to work out. I don't have to do anything different from my business as usual. Let's just plow ahead. And then the third biggest bias that we have observed is what's called the status quo bias. And so the easiest way to explain the status quo bias is, humans are really good at evaluating and scrutinizing the new things. So if I put in front of you a concept design for, let's say, a geo exchange system, and you're not familiar with geo exchange, it's your first time seeing this, you're going to be able to point out all the things that you don't like about it relatively quickly. And there is no perfect technology. Every single technology has pros and cons, and you're going to correctly identify the cons. What the bias is that most people will revert back to the business as usual on the false assumption that that is the safer thing to do in terms of their decision-making process. And the bias is that we're not doing the same level of analysis, and we're not scrutinizing the business as usual to the same level of detail and rigor that we do with the renewable. And so we're basically positively reinforcing the business as usual and kicking the can further and further down. And it's just really important that we introduce this elephant so that when we come across it in future projects, or maybe even later in this presentation, we can just kind of remind ourselves, like, wait a second, am I looking at this critically, or do I have some subconscious bias that is making me kind of turn my nose away at this type of solution? So it's really important that we although we're talking about engineering and technical things, that we remember that we're dealing with human beings, and human beings are much more complicated than a heat pump, believe it or not. So speaking of heat pumps, let's start off with air source heat pumps. Now we can get into the technical bit. We're going to start with air source heat pumps because heat pumps in of themselves are a critical piece of technology that enables a lot of the other technologies we're going to talk about today. So let's talk about an air source heat pump and really talk about how a heat pump works. So most people don't realize that their refrigerator is a heat pump, or that window unit air conditioner is a heat pump. And if you don't believe me, all you have to do is put your hand on not the front end of that air conditioner, but on the back end of that air conditioner, and you will feel a tremendous amount of heat being blown out of that unit. And you can magically change your air conditioner into a heat pump just by simply picking it up and turning it around backwards and putting it back down. And that is so what the heat pump really is something in thermodynamics called the refrigeration cycle. And don't worry, we're not going to go down the thermodynamics rabbit hole, but I just want you to understand at a fundamental level that an air conditioner and heat pump are really the same piece of technology. And what it's doing is it's using a compressor and a refrigerant to essentially make one surface really hot and another surface really cold. So just quick thermodynamics second law lesson here. Just think of heat like a waterfall. It can only flow down. And so when we're talking about heat, what I mean is heat can only transfer or move from a hotter surface or object to a colder one. You can't, the heat won't flow from a colder object to a hotter one. It's a one directional type of relationship. And so when a heat pump creates a really hot surface and a really cold surface, what it's doing is the cold surface is then able to absorb heat from things that are warmer than it around it. So in this case, it's air. So that cold surface you put outside your house, and the cold surface is absorbing the heat from the air, and then it travels through the heat pump. It gets boosted up by the compressor into a really hot surface. And then let's say in a single family home with a forced air system, then you're blowing air over that hot surface, and the air is colder than the hot surface. So the heat then moves from now your hot surface to the air. And so you are quite literally pumping heat from the outside of your building to the inside of your building. Now, what they've done, like with the unit on the left on the screen here, is they've just taken that window unit and essentially chopped it in half, put the cold surface outside, put the hot surface inside, and then reconnected all the plumbing essentially. And so now you can move heat from the outside to the inside. Now, if you want to go into cooling mode, you can't physically pick up the units and move the plates around. So what they do is they just put in a reversing valve essentially. And now instead of having to physically move the hot and cold plates to different places, they can just reverse basically the process. And now the cold plate becomes hot and the hot plate becomes cold. And we're now absorbing heat from inside your building and then literally pumping it outside your building. Now, anyone that has looked at a heat pump, a lot of people will talk about the COP, which is called the coefficient of performance. And all you need to know is that this is just essentially a way to gauge how efficient that heat pump is at moving heat from the cold surface to the hot surface. So most heat pumps, a lot of people say it has a COP of 3. And what that means is that for every 1 kilowatt hour of electricity that heat pump is consuming, you're going to get 3 kilowatt hours worth of heat on the hot side of that heat pump. But anybody that remembers the fundamentals of physics, we cannot create or destroy energy. So how does this work? And it's even more confusing when heat pump salespeople talk about 300% efficient heat pumps. So how is that possible? How are we getting energy kind of created essentially? Well, the trick is we're not breaking the laws of the universe. What we're doing is, if we're getting 1 unit of electricity that's turning into 3, we have to figure out where the other 2 is coming from. And the other 2 is coming from the cold surface, the source. That's why they call it an air source heat pump. And that's where the heat source is coming from. So if I'm getting 3 units of heat out of my heat pump and I have a COP of 3, that means 1 of the units is coming from the electricity, but the other 2 is coming from the source, in this case, air. There are some really great manufacturers out there that make some really highly efficient heat pumps that are able to get COPs greater than 3. And there's a ton of engineering that goes into optimizing and trying to improve the efficiency and performance of these heat pumps. But the number one factor that can determine if a heat pump is going to be efficient or not, or to improve the efficiency of the heat pump and jack that COP as high as possible, has nothing to do with the heat pump itself, and it has everything to do with the temperature of the source. So in this case, air. So as you can imagine, on a really, really cold day, an air source heat pump is going to be less efficient than on just a somewhat cold day like today here in Toronto, where we're hovering, just around 0. And there's nothing that the heat pump technology can do to change the temperature of the air. And all you have to do is look at your weather app and look at how much the outdoor air temperature changes over the course of just a 24-hour day. And that means that the efficiency of your air source heat pump is essentially riding that wave of temperature differences, and its efficiency, and therefore its price to operate, fluctuates with the temperature of the day as it goes on as well. So that is how a heat pump kind of works real quick, and COP and where it gets the energy from the source. So these we're seeing are mostly used in, like I mentioned at the beginning, in smaller density projects. We're seeing them in larger scale projects as well, but you really got to do your engineering math and figure that out. But one of the pros is that they are typically a lower cost, first cost option. And there are some limitations though with regards to space and structural load. They're kind of big, heavy, sometimes loud devices. And then, as I mentioned, the cold weather operation is highly influenced by in terms of how efficient that heat pump is. Let's get into geothermal, the category. There are probably 6+ different flavors of geothermal, but we're going to talk about the one that is most prevalent that we're seeing in the real estate development of the world, which is geo-exchange. And I just really want to emphasize and underscore the word exchange. So remember the heat pump? We're talking about the efficiency or the performance of that heat pump is highly dependent on the source at which it is pulling heat from. Well, the ground is a much more stable and predictable source of heat. So instead of riding the outdoor air temperature roller coaster, we're going to have a much more lazy river type of experience in terms of the source that heat pump is pulling from. The challenge is that the source is typically hundreds of feet below ground. So when we're doing these geo-exchange projects, the boreholes that we're engineering are anywhere between 600 feet and 1,000 feet down. So this is not a DIY project. So this is pretty heavy duty type stuff. A lot of the technology is coming out of the oil and gas industry and is being modified to be more cost effective for the real estate industry, because obviously we don't have oil and gas money here for residential real estate. But what I mean in terms of exchange, though, is that geoexchange is not a true source of energy in that you can deplete it. So every megawatt hour of heat that I pull out of the ground and push into your building, I have to put back at the end of the year. And so this is in the early days of geoexchange, this wasn't well understood by operators, and there are some unfortunate examples of bore fields that basically they froze. You know, they just pulled so much heat out of the ground and weren't putting enough back in that the bore field essentially became a giant block of frozen rock and was useless as a heating resource. So you might be wondering, well, where do you get all the heat to put it back in? And the trick is we do that by cooling the building in the summer. So I'm going to say something that sounds a little bit annoying, but there's no such thing as cooling from like an engineering thermodynamics perspective. I know it sounds super annoying, apologize, but it is the truth. And so what I mean by that is what we experience as cooling is really just heat leaving our body. And so when we're cooling a building, all we're doing is just moving heat from the building to out of the building. And we just experience that as cooling. But from an engineering perspective, we're just simply moving heat either towards you or away from you. And we experience that as heating and cooling. So in a geoexchange system, you need heat in the winter. We're going to take that heat out of the ground. Again, we're going to put a cold plate touching the water coming from the ground to absorb that heat, push it into a hot plate inside your building, and then we're going to simply reverse that process in the summer. So we're going to take all that heat that your building is absorbing from the sun and the people inside of it, and we're going to absorb that in a cold plate in your building, and then we're going to upgrade that and pump that into a hot plate that then deposits that heat beneath your building in a massive geoexchange bore field system. So that's geoexchange kind of one-on-one right there. There are other versions of geoexchange. I think some people might be familiar with horizontal systems. These similar principles, similar idea. It's just you need horizontal real estate now. This is why you see these more on rural properties, for example. It's more cost effective to have a local excavation company dig out big trenches and put your big coily PEX pipe in down there than to have a drilling company come in and put a borehole in. But when we're dealing with more dense urban environments, we do not have fields to put horizontal loops in. And we also, the big difference is when we're doing vertical geosystems, we don't want dirt. In the geo industry, we call that overburden. Overburden is a pain in our butt. We do not want overburden. We want rock. And so that comes down to some of the pros and cons here. And the con that I'm talking about here is that this is a site-dependent resource. We have a pretty good database now. We also have a really good network with drillers all around Ontario, and we're starting to kind of broaden our horizon across Canada. But to try and understand what locations have good geology and which ones have more challenging geology so that we can assess the cost essentially associated with drilling a geo asset out. Another massive con, as you can imagine, this is not cheap to install. But this is a much more efficient use of the heat pump technology. We're going to have way better COPs, more consistent COPs, more predictable COPs. And so you really now need to look at that second layer, which is the business model, the financial feasibility of these types of systems in order to determine, a yes or a no. So here's a great example. This is a 145 borehole project at 850 feet. And this is out in Etobicoke. So, and I think we're up to over 30 projects of this type to date now. So in various states of study, design, and construction, almost exclusively here in Ontario. Ontario has pretty good geology for this. So, and what we're finding across all of our feasibility studies that we've done over the last 5-6 years is that a real majority of them, geoexchange is the best performing in terms of a levelized cost of energy analysis. So that brings us to another source that we can use heat pumps with, which is wastewater energy exchange. And I know what you're all thinking, poop, I get it. There is that there, and I know it's uncomfortable to think about it. It's also warm, but that is not the majority of the flow going through the sewer pipes beneath our streets. It's shower water, it's dishwasher water, it's laundry water. This is a lot of domestic hot water that is just going into the drain relatively quickly. Think about when you're in the shower, how long it takes a drop of water to go from your head to your toes. A couple seconds, 5 seconds. Well, you paid for that water from the municipality, but you also paid to upgrade that water from sub 10 Celsius up to 65 plus Celsius. And you used it for about 5 seconds. So wastewater energy exchange systems are a really great opportunity to capture a lot of that domestic hot water energy that you've already bought and paid for and put it back into the system. So we can do this at two different scales. We can do this at a building scale, like a mid-rise or high-rise in terms of density, where we're capturing the heat out of the wastewater before it leaves the building and enters the municipal system. But the biggest opportunities are like trunk sewers. So whenever you're looking at just how much wastewater does a building produce versus how much energy do we need, the ratios will not line up. I'll save you the math. What we're typically seeing is, putting in one of these systems to put a massive dent in the GHGs associated with the domestic hot water production. But the space heating, there's not enough energy coming out of that wastewater to do the whole thing. But if you have a trunk sewer, you absolutely could do the whole thing depending on the size of that sewer. And so that leads to one of the major cons is that it's a highly site dependent resource. So one of the first things we check when a developer asks us, what are our options? We always look at wastewater energy transfer as one of them. And depending on the jurisdiction, we will be able to either have easy or less easy access to what is in the right of way from a wastewater perspective. And we can quickly assess just on the size of that pipe if it's worth spending time investigating in more detail or not. But if it is worth investigating, if you have a good sized pipe going by your building, this is another really strong front runner in terms of providing a very cost-effective cost of energy for the heating systems. So back to the COP of the heat pump, the source of that heat having the greatest impact on the efficiency of that heat pump and therefore the cost to operate that heat pump. So we went from air being a bit of a roller coaster to geo-exchange being a lazy river, to wastewater being basically a really warm, lazy river. So if you have a trunk sewer, we're able to get even better COPs out of a wastewater energy system typically. So these are really strong on the financial side as a result. And here's a really great example that a mega project doing this out in Vancouver with our friends at Creative Energy doing this type of work. But there's another great example here in Toronto. The specific question about using waste heat from an ice rink in combination with the geofield, we're doing it. We're doing it out in Whitby as we speak, which is a really exciting project on the Whitby Sports Center. So this new massive, going to be beautiful facility, 2 rinks. I think it's got 3 or 4, basketball courts and a giant field house, massive swimming pool, community center rooms, the whole works. And that's just the building, the whole park. If you like pickleball, my goodness, I lost count how many pickleball courts are going in that place. But they had a challenge of, we want this to be net zero. And we figured out the way to do that essentially was to take the heat coming out of that ice rink in combination with a bore field, heat recovery chillers, just let's say high efficiency heat pumps and some backup electric boilers. And that entire facility will be able to operate with 0 natural gas. There is 1 natural gas pipe going for the entire facility, and that's simply for the backup electrical generator, which is like a life safety factor. So that kind of goes into a different bucket. But in terms of the day-to-day operations, we were able to design that facility to be completely net zero by using that waste heat from the refrigeration or the ice making system in combination with a geo system. So that's a really great example. And this was, as you mentioned, Gabby, at the beginning, it's a lot easier to do this stuff when we're dealing with sheets of paper or digital paper, essentially designing things. Retrofits are going to be much more challenging and expensive, obviously. but the heat is there at an ice rink. So if you can come up with a concept that is financeable, you basically have that free heat as a resource to decarbonize the other things that need heat. So yeah, these types of projects like district energy, and we'll get to district energy in a second, because typically where the heat is being produced, like a data center or a rink, is not always right beside the thing that needs heat. That's kind of like the big catch-22. It's like, oh, I have all this like heat being wasted over on this part of my community, and I have all this part over here that needs heat in the community, but they're not beside each other. So this is where district energy really helps enable these types of opportunities. As you can imagine, the operating costs are going to be pretty low because you're not paying for the heat in of itself. And depending on how you're doing your carbon accounting, you can have significant carbon reductions here. In capital, the cost of these things can be dependent, but that's where scale is your friend. And here's a really good example in Europe, where Facebook located actually 2 of their data centers in Denmark. And it wasn't just because it's a fairly central European location. It was because they were able to contribute to their climate pledges by building their very power-hungry facility in a jurisdiction that has a huge amount of zero and low carbon electricity. But on top of that, while they're spending money running the chillers to cool their data centers, they are offsetting some of their electricity costs by selling the heat back to the local district heating utility, and then the local district heating utility is now using that heat to decarbonize their district heating system, because the heat coming out of the data center is essentially zero carbon because it's being produced from the data center, which is consuming zero carbon electricity. So it's a really great synergy of private and public infrastructure and heating and cooling and power, working all together to create these types of outcomes. We're also working on a really great project here close to home in Hamilton, where we're going to be taking the heat out of the steel industry to decarbonize huge portions of downtown Hamilton. So this project is in study. HCE, which is Hamilton Community Enterprises, is running this project on behalf of the city. They're a city-owned organization, and they have lots of literature available on their website. So I encourage you to check it out if you're curious. Okay. This is the technology where I'm going to remind us about the bias slide. This is a very controversial technology. I make no bones about it, but I think it's important. I've gone on a biomass journey, so to speak, over the last 5 years to deepen my understanding of what this technology is, where it comes from, and how it is accounted for, essentially. So I'm going to do my best to share as much of that 5 years journey in 5 minutes here. So. Biomass is, in its most common form, it's a category like geo, but its most common form is typically wood pellets or wood chips. Pellets are typically used on smaller scale projects and chips on larger scale projects. And this is simply due to the business models, economies of scale, but also when you're handling chips, you need a lot more fuel handling equipment in terms of like conveyor belts and all that good stuff. And so that costs money. And in order to make that financial equation make sense, you typically need a fairly large facility. You're not going to be able to afford all that type of stuff for a smaller project. Because these projects are better at scale, then they also play nicely with district energy systems. And you will see this all over European, Scandinavian countries, which are all kicking our butts royally at decarbonizing themselves compared to us. But you also see some great examples out west, and we'll give a shout out to that project shortly. But the biggest thing that I learned about biomass was where the fuel itself comes from. So I got a tour of a lumber mill up in Halliburton, run by Halliburton Forest, which is the first sustainably certified forest products producer, which is really cool that it's here. And you just kind of take for granted when you go to one of the big box stores, you got 2x4s, 2x6s, and all this lumber, and they come from trees, but there's like this disconnect about a tree is this shape and the 2x4 is that shape. And you don't really think about what happens to the rest of it or what that ratio is. And so when I went to this lumber mill, I saw all the cool stuff I was expecting to see, But then when I went around the back of the building, that's when my eyes got really big, because there was two humongous conveyor belts coming out the back of this lumber mill, with bark chips and dust, basically the byproducts of turning a round log into dimensional 2x4s, sixes, etc. And as you can see, the ratio is not as awesome as I think you would hope. So there's going to have to be some sort of reckoning as we move forward here, because I think the sustainability world with buildings is starting to recognize the value of mass timber buildings. We're using a renewable resource to build our buildings. We're sequestering carbon with mass timber buildings rather than emitting carbon with concrete and steel produced buildings. But our trees don't grow in squares. So if you're going to go down that pathway, then we should really be using the entire harvest of that log instead of just the parts that we want to build buildings out of. And this has been studied ad nauseum. I encourage you to do your own research, but the best place for those what are called residues is typically in district heating or heating applications. So this is where this comes from. There's no new trees being cut down to fuel a biomass power plant. What's unfortunate is we used to have 15 lumber or pulp and paper mills here in Ontario. We're now down to, I think, 3. And what's happening is that the lumber demand hasn't slowed down. Housing is just increasing. And I won't divert into the housing crisis here, but we're only going to be building more homes. And as we start to decarbonize and start to understand embodied carbon, we're only going to be using more lumber to build those structures. And what we should really be doing is looking at it in a much more holistic way, essentially to utilize that biomass. So there's some great examples of this, like I said, overseas. But Simon Fraser University, operated by Corix Utilities out west, is a really great homegrown example of using that waste biomass coming out of these industries for decarbonization purposes. They have great efficiency. They're really unique in that you can do cogeneration with a biomass. Like, you cannot create power from a geo-exchange system or a wastewater energy exchange system, for example. But the temperatures that a biomass facility are able to produce are in the same ballpark as the other forms of power plants. So we can create steam and turn a turbine and generate electricity, and we can then take also the heat out. So we're getting a cogeneration aspect of this. But as you can imagine as well, we need some big space for this. So you're not going to be putting one of these in any sort of downtown environment. So there's, like I said at the beginning, there is no perfect technology out there. Every one of them has pros and cons, strengths and weaknesses. That's why we have the choice overload bias challenge in front of us. But the attempt is to try and figure out which one is the best fit for the respective project and strategy. When we do a study, we typically do what's called a levelized cost of energy analysis. So the levelized cost of energy is, we will build out like an energy model. It's not a building energy model. It's like a system energy model. So we have our own modeling to do that. And we'll build that out over 30 years so that we can capture the life cycle of that asset, that investment. And then we'll also build out a cost model that reflects that same duration. And we'll do that for your business as usual to combat the status quo bias, because the only way to combat the status quo bias is to scrutinize the business as usual the exact same way you're scrutinizing all the other options. It has to be fair. So we'll do that for the business as usual, and we'll do that for the renewable scenarios as well. And we take the total amount of dollars for each scenario and divide it by the total amount of megawatt hours that scenario needs in terms of energy. And it gives us a dollar per megawatt hour number that we can compare the business as usual against the other options. And so in that cost model, we're able to capture not just the upfront capital cost, like the sticker price of all this stuff, but also the operating costs of what's it going to cost to operate that technology over 30 years, the maintenance costs over 30 years, the fuel costs, which includes electricity and the carbon tax in there, recapitalization, which is a fancy word for stuff breaks. So, at the end of 20 years, you need to make sure you're budgeting for stuff to be refurbished or replaced. And so that holistic cost model goes in, and we can now give the owner a way to take apples, peaches, pears, and plums and give them an apples to apples comparison. So the actual number in terms of the dollar per megawatt hour is not really what's important. What's important is what's the difference between the business as usual dollar per megawatt hour number versus all the other ones. And, when I first started this journey, I was, it was always a foregone conclusion that the renewable option was going to be the more expensive one. And I spent a lot of time trying to explain the virtues, the non-financial virtues of going down the renewable pathway. But I remember this vividly because it was COVID and I was in my slippers in my basement when we did our very first study where one of the renewable scenarios actually came in at a lower dollar per megawatt hour number than the business as usual. It was like 3-4 years ago. And because my whole career up to that point had been the opposite, that kind of hit me really hard. And that is frankly just been the beginning of a whole new market opening up where every quarter we see more and more projects where the renewable option is just the better investment. End of sentence. Oh, by the way, it also got 80% of the GHGs out of the building. But just from a pure raw investment perspective, if you were to invest in the business as usual, this would be a poor investment choice than going, let's say, with the geo exchange system for that specific project. And that's been really exciting to see. Now, like I said, we used to work mostly or almost exclusively in the medium to high density space. But over 2023, some of our high density clients also do low rise developments. And they said, hey, we really love what you're doing on the high density stuff. Can you help us figure out the low density? And what was really exciting and interesting for us, I'm going to nerd out here for a second, is we were wrong. We were so wrong. All the stuff that didn't make sense in high density land and made sense was not all flipped on its head, but a lot of our assumptions were kind of corrected through our modeling process. And whenever that happens, we drill down into the numbers and quadruple check everything and even call a couple of friends, so to speak. And so what was interesting on the low rise side is that air source heat pumps actually make a much better financial case in low rise, and they're really actually poor on the high rise side of things. So that was a really interesting learning for us. The other one that was really interesting, and this kind of came out of a client request. So in order to make sure that we don't bankrupt ourselves, we have to cap the amount of scenarios we do in these studies. So we make the business as usual mandatory. It's non-negotiable. If you ask me to do a study without it, I will politely decline your study, because if we don't, we're going to run into the status quo bias all over again. And then so we typically figure out what are 4 other scenarios to do. And they really only had 3 that kind of were interested and made sense. So we just said, why not? Let's just throw in the all electric scenario. Like we just completely ditched natural gas for this kind of low rise community. And it was singles, semis, a little bit of town, and a little bit, I forget what they're called, but the ones with the garages in the back. You can tell I'm not a developer. So really kind of low density stuff. And the all electric one, we were just like, that's totally going to have a high levelized cost of energy. It was the lowest. And the biggest, and we were like, this can't be right. Like all of our assumptions are being contradicted through the numbers here. So drill down into the numbers, and the savings that we were seeing in this levelized cost of energy model were actually because there was 0 capital being deployed for a complementary natural gas system. So it was just like there's 0 natural gas. And so when you're paying your natural gas bill, there's a capital charge where you're basically paying back the cost of putting the pipes down your street into your house. Well, it might only be like 20, 30 bucks a month or something like that, but over 30 years, that builds up. And so that's where the massive amounts of savings were that really dropped that down. The next challenge, though, was what does this mean for my electrical panel? And our scope was exclusively thermal, so we didn't have the numbers on hand when they asked this question, but we just did some quick back of the envelope math. And we're like, well, what size panel do you typically put in? And they're like, yeah, about 120 amp panels. And I'm like, you're probably going to need like over 250, like a 300 amp panel. And that's without an EV charger for the EV in the driveway. So if you're adding an EV, you're probably looking at 400 amp panels in the scenario, because we're putting a huge load on that electrical capacity with the heating and the domestic hot water plus you have all your plug loads. So you're having induction stoves, electric clothes dryer, electric washer, electric everything. It just adds up. So now at the house, you have big panels, but now what does that mean for the local transformer station? So, that was the next question. And they have the relationships with the local distribution companies. So they were able to take all of our math and put it in front of the LDC. And we just got lucky on this project that there was a huge amount of capacity available at that local transmission or transformer station. But that's not going to be the norm in my estimation. I think a lot of our electrical infrastructure is close to, if not tapped out. So there's going to be a lot of challenges with these that go beyond just finding the right solution. So again, that technical, financial, people, you need all three layers of a project to be successful in order to get the green light.